Okay, so we mentioned a certain SU3 projection of E8, right? So this is a 2D projection of E8. So what we're going to do is I'm going to show you a certain rotation that would give you a nicer projection of E8 on a two-dimensional plane. And we'll call it the E8 magic star. So this is something that was studied by Piero Chiarini originally. So the new paper that I came out with on exceptional periodicity is a generalization of this structure. But it's nice to start with this. Okay, so I'll just go ahead and draw it here. Okay, so we have these series of points. And mind you, we are projecting down from 8 dimensions, okay, onto a plane. So these are, they're 248 objects that I'm projecting onto a plane. So there's going to be 246 points here that are going to be either overlapping or just on their own. Okay. So the reason I'm connecting these is because algebraically, they're actually related. Okay. So we have a triangle there. We have a triangle here. So it looks a lot like, say, the Star of David, and well, your name actually is David. So this is appropriate. But this is actually a geometrical projection. Okay, and these points are very important because this is giving you this SU3 projection. Okay, so we have this SU3, typically, as you know from quark physics, the gluons, they have an 8-dimensional kind of symmetry to them.
3 squared minus 1.
Yeah. So,
SUN.
So you can think if we have, well, typically we can expand it in terms of, let's say, this E8 here. So if we write the SU3, so I'm going to be essentially slicing E8 in a certain way. So this is the E6 here. And so this is called a grading. It's just one way of slicing it. So there's a mathematically precise way, of course, stating what this is. But we will go ahead and just ignore that for right now. Okay. Let's just go ahead and put a bar there, okay, to denote this triangle and this other triangle here, okay? So these 27s, these denote 27 vectors that have just been projected on the plane, okay? So this first 3, you can think of them, you know, as one of these triangles. And these other 3 here, so this is 3 27s that are here. So I'll just go ahead and write the dimension here.
Some dual triangle or something?
Yeah. So let's go ahead and denote them this way. Okay. So as you see, this looks a little cryptic, but when you draw it this way, it's pretty obvious. Okay, so the E6 actually is here. Okay, so that is 78 dimensional here. Okay, so that is the E6. So I'll just write 78 for that. Okay. And the SU3, so there are 8 dimensions to work with here, but we're using 2 of them to project this picture. So therefore we have the remaining 6 here. Okay, so I'll just write a 1.
So 2 for the axes of the plane,
yeah,
and 6 points.
Yeah.
Right.
Right. So if we have these axes here, and if we go ahead and we add up the total dimensions, okay, so we have these 27s plus the 78 plus these outer 6 plus the axes that is projected on, and it will recover the full 248. So.
Right.
Yeah. So if we look at it algebraically this way, we have, this is the picture, and here we have 8, and we have the 327, so we can actually come to 248 total. Okay.
Sweet.
So here, that's one way to split up. This is actually really enticing in string theory. So this is when you're looking for Calabi-Yau, you want to find a Calabi-Yau space that exhibits this kind of symmetry, because E6 is a very it's a very helpful symmetry group in terms of grand unification. Okay, so another way to look at this picture, we mentioned Freudenthal triple systems and these extremal black holes, right? So this is actually referring to a different slicing, but I'll show you what that is. Okay, so we have these objects here. Okay, so let me go ahead and let me show you what a column would look like here. Let me give this a different color here. Okay.
So you have that subset.
Yeah, so this is identifying a 1 plus the 27, and we have a 27 plus 1, right, which is a 28, and another 28. Okay, so both of these together are giving us a 56-dimensional space. Okay, so this is typically used within supergravity as a charge space for a 4-dimensional black hole, extremal black hole. So which is very nice. And we can say, okay, that's very nice, but this space, what's the symmetry of it, right? And of course, we're always curious about the symmetry. So let me go ahead and let me use green here. Let me kind of stick in the theme. So the symmetry of that space, which actually has an algebraic structure, okay, is this here. So we have 27, 78, and 27, and we use one of the axes that we projected onto. So we actually have 133 dimensions of E7. Okay, so we have another exceptional symmetry. So all we do is slice vertically and we see E7, okay? And in here, we know that this 78 is the E6. So these are exceptional items. So in the middle, we have E6. We take this vertical strip here and we get E7. And E7 describes the symmetry, right? These rotations and these general transformations of this space here, which is the 56. Okay, so this is called the fundamental representation of this E7 here, so which is very nice. So we can denote this as a charge space, right, of some sort. Okay. If we want to give it a physical interpretation, right? So mind you, I'm not a physicist, but I just happen to know these things. And you've seen them probably before in studies with your advisor. So what about extending it further? Okay, so if we have an E6 symmetry, and the E6 symmetry is actually the symmetry of one of these guys, okay? So this is acting on that object right here, and this is actually a certain algebra, which I mentioned is this very special algebra, which is we call the exceptional Jordan algebra. Okay. So in this case, we can say it's over the Octonians.
And this was that unique quantum mechanical algebra that was discovered back in 1934, but no one uses these Octonians.
No. So it actually came up naturally here. It's on the vertices of this star. So remember, this is just a projection of E8. So it's naturally coming about in E8. So you naturally have these this exceptional Jordan algebra that gives you this sequence of quantum mechanical theories that terminate at this algebra. So you have this as the maximal quantum mechanics over Octonians in some sense. Okay, and this is naturally popping up in this projection of E8. And this symmetry here, you can think of as the symmetry of this algebra that preserves, as you know, something called the determinant of a matrix. So it's this invariant that's given by this E6 in the center. And this whole column here, as let's just call it the Freudenthal triple system, okay, so I will denote it FTS, okay, for short. So the symmetry of this algebraic structure, okay, so what we do, I'm just going to write it as a 2x2 object, okay, and so we could think this has 27 dimensions there and another 27 here, okay, and there's a single dimension there and a single, so I'm just writing it in a form so you can see where the dimensions go. And this usually gives you the charge space for a ionic black hole. Okay, and these are extreme black holes. So you probably heard this kind of terminology, but it's so simple when you write it in terms of this star here. So as far as Garrett's theory goes, so he assigns quarks to these spaces here. And if we flesh them out we can actually, let me expand it in a sense here. So this 27, we can identify 3 degrees of freedom here, plus an extra 24, okay? So if this is an algebraic object and we diagonalize this thing, we can get rid of these off-diagonal degrees of freedom and focus purely on the 3. So these 3 here are what can be found in Garretts model as these X bosons.
I see.
So we can say if you use Garrett's Elementary Particle Explorer online, and he'll denote them as X1, X2, and X3. Okay, so these are very interesting. The question is, what are these things? So, and what are these, right? So it turns out that if you assign quarks in here, right? So if you have quarks, then these particles would be related to that. So if you return to this quantum mechanical formalism, we can ask, wait, these are like the diagonals, right? So these are, if we diagonalize the matrix, and these are giving certain special directions. Okay, so these special directions are almost freezing these guys. So it may be that they're not a problem after all. If they freeze, so something's happening here where these directions are being frozen, and they're encoding these internal degrees of freedom along those directions. So maybe these X bosons in light of E8 aren't so bad after all. Right. Okay, so this is just a model. It's not claiming to be a grand unified theory of everything, but it's just these remarkable coincidences that come up. So in light of that, we can assign actually this 27, even within the extremal black hole formalism, you can look at a certain 5-dimensional black hole that has a charge space with just one of these 27s. So it's funny. So you can isolate this thing, and it really goes back to that intuition that maybe there's not such a difference between these elementary particles and this extremal black holes, right? I mean, these are different theories. I'm just looking at from a mathematical perspective, right, which is all I can do. Yeah. And I'm just noticing these coincidences. So what's in here in these 24, as you see, and we know, we can break it up into 3 times 8, right? So these would be 3 copies of the octonions. So these 3 copies of octonions actually...
So we could put these 27 things in a 3 by 3 matrix, right?
Yeah, we can put them in a box. So box it up in a 3 by 3 matrix. So we can look at, I'm just writing the dimensions here. So we have an 8, 8, and 8, 1 degree of freedom, 1 here and 1 there. So and then across from it, these are just the conjugate. I'm just going to draw a point here. Okay, because they're going to be, it's the same information that's repeated. It's like the reflection of these. So I'm just going to draw points to show that we exhausted all the dimensions. So 3 times 8, 24, 25, 26, 27.
So we see we have 3 real components along the diagonal, and then the off diagonals you could represent with octonions, right?
Yeah. So what has been done with a certain form of a generalization of this algebra, the octonions, we have Cole-Fury's work, where she identified actually the matter particles, the leptons, and the quarks from the Standard Model with a certain complexification of this. So if that's done, we can actually assign it to these off-diagonal degrees of freedom. So the matter particles, in a sense, live in here, right? And here in the center, we'd have the force fields, which are the gauge fields. So there'd be quite a few degrees of freedom, but...
And it's kind of funny because we do have 6 different quarks in the Standard Model.
Yeah. There's actually, so we have 3 generations. So you see multiple copies represented here. I'm also, so looking here, we can see matter, force fields. I'm not sure what these outer ones are yet, but it'd be interesting to just explore it just from a mathematical perspective. And it was also possible, so this star is quite handy. it's also possible to extend it. So that was the topic of the new paper that I came out with Piero Truini and Alessio Morani. So in extending this structure, we went to some higher algebras that are no longer Lie algebras. So it falls out of this classification because it fails to obey this identity called the Jacobi. Yeah. So they're more general, and they're reminiscent of these vertex algebras that have come up in string theory before. Actually, they were kicked off by string theory. You know, string theory actually kind of defined this branch of mathematics. So it's pretty rich. You know, you have this interaction between physics and math, and you can ask, you know, like, who's feeding who?
Yeah,
right?
it's
like,
going both ways.
It's going
it's
both
a conversation.
ways. Yeah, so it's leading somewhere. So this kind of mathematics is broadening physics, but it's also broadening mathematics at the same time. So this interplay between these two disciplines is leading to a more unified way of looking at mathematics, but also a unified way of looking at physics. And it's really handy because you can see in the math department, this kind of mathematics is typically not related to some other lattice type mathematics. You know, you have certain sections of the department, certain researchers that don't communicate with each other, but in light of physics, you can ask questions about a physical system like a black hole, and you can ask, you know, what's its entropy, right? And you can write out some sort of modular form for it. This would be one branch of mathematics that has its researchers and mathematicians that specialize in that. And you can ask a different question: what's the symmetry? What's the U-duality, you know, symmetry of this black hole? And that leads you to this branch of Lie algebras and its generalizations. So this is I would say the root of this infinite structure that we found, and we can go higher, and we can actually reproduce this diagram out to infinity. And all that increases is the dimension here and in the middle, and these stay the same here.
This is pretty interesting as a physicist because usually we use Lie groups a lot of the time for describing, you know, a lot of different things. So, you know, the standard model is based off all these groups, and we've been playing, you know, there was a lot of efforts trying to use E6 for grand unification. You know, there's Garretts Model, but I mean, what's interesting is what you're telling me is that you found not only does E8 have this magic star representation, but once you use this representation, it's kind of a template to find an infinite tower of new mathematical objects that I wasn't even aware of, right? And I don't think the mathematicians weren't either.
I don't think,
right?
This was, of course, fueled by physics.
Yeah.
So what actually was the inspiration for it was going back to the discussion about these extended Yang-Mills theories, up to 14 dimensions. So there was a certain pattern that inspired me, and I discussed it with Alessio and Piero Truini. And after that discussion with Eric Weinstein, it kind of kicked off this idea that there could be an infinite tower that includes not only E8, but higher dimensional theories beyond E8, which is nice because in string theory, you have an E8 cross E8 symmetry. So there's two copies of E8 in the heterotic string, which isn't described by a single copy of E8. However, we do see multiple copies if we go further in this structure that is called exceptional periodicity. So the naming came about because it's reminiscent of a structure in mathematics called Bott periodicity, as we discussed before. So the Bott periodicity has to do with these rotational groups. And actually, these rotation groups act on spheres. So this kind of, these symmetries that arise with the spheres are periodic every 8 dimensions. So this is very similar. This contains the rotation groups, but it also contains this structure that's reminiscent of spinors. So this is much nicer for the investigation of physical theories. And it turns out that it does make contact with these higher dimensional lattices, which are used in the heterotic string and even beyond the Leach lattice. So
one thing that I really like about this is that, you know, with string theory, it's a great theory. You have all this mathematical formalism, but it seems that there's this supersymmetry that relates the fermions to the bosons, you know, the matter particles and the force carriers.
Right.
But with supersymmetry, you have to say that the mass of the two superpartners is identical. But so it seems that this supersymmetry has to be broken at our energy scale. And then at some higher energy, the symmetry could remain. But I mean, it's interesting because it doesn't seem that this necessarily has to do anything with supersymmetry, but you have these bosons and these bosonic and fermionic degrees of freedom. And it's interesting because it has a lot of this underlying structure that string theory is based off. But from your perspective, it's just a mathematical formalism.
Right. And if anything, it exhibits an exceptional quantum mechanics that arose in 1934. So in extending this magic star to exceptional periodicity, which also has magic stars. So these are certain star generalizations of this. They have the same shape, but these increase in dimensions according to these increased spinners that arise along with their rotation groups. So it would be interesting to investigate these higher exceptional periodic structures and ask, hey, if this E8 level, if these gratings exhibit some symmetries from Superyangmills theories, right, up to 14 dimensions, say, if we go beyond this, can we investigate theories, say, in 22 dimensions, for instance, right, or higher? We can investigate, say, 26 dimensions, 28, right, 30 dimensions. So with these exceptional periodicity gratings, we actually have a structure that does have spinners. So it kind of begs the question of what to do with it at this point, right? So if we can relate some kind of extended Superyangmills theories to this, then that would be totally awesome, because that's something that hasn't been done before, because as mentioned in Sezgin's paper, he stopped at 11-3 signature, right? So 11 space 3 times, and he tried out the 12-4 signature, and it didn't quite work. But what I noticed is that at this 12-4 signature, there is no grading. That means that there are only 2 pieces, so you need at least a 3-piece, a way of splitting this object up. So in this exceptional periodicity framework, we can go on, and it ends up repeating once again with a single time direction, 2 times directions, and 3 time directions if we look at these non-compact symmetry groups. So it's open to study, and it's actually a very nice structure that was surprising to look at. But in generalizing this star, it turns out that these are no longer Jordan algebras.
Right.
So what happens in this case is we have another object. So we go from Jordan algebra that are 3 by 3, okay, 3 by 3 matrices. These get generalized to something called a T-algebra. And these are 3 by 3. So it's very nice. So one of the famous mathematicians, Vinberg, actually had studied these T-algebras, and we were able to relate the extended algebras that arise in these stars with these algebras that have been investigated previously by Vinberg, luckily. So we have a nice way of expressing the symmetries of these T-algebras in terms of these higher algebras that generalize these exceptional Lie algebras. So it's pretty cool. So these Jordan algebras, we can think of it this way: Jordan algebras to Lie algebras is to T-algebras going to these exceptional periodicity algebras. Okay, so that's the comparison there. So the question is, do these define some higher dimensional quantum mechanical theories, right? Are these generalized quantum mechanical theories that lead to these higher symmetry algebras, right? And if so, is it possible to relate these? Okay, since we can see the structure of some Superyangmills theories here, what comes up here is, are there some extended Superyangmills theories here, right? So that was the big question that came up at this point, but it's very early in in the progress along these lines, but I was just giving you the gist of the utility of this kind of projection.